Welcome to Talk Tensors.
Glad to be here.
On this deep dive, you are covering a classic and seminal computer science or machine learning paper.
Yeah, a really massive one today.
Exactly. Today, we are undertaking a highly specific mission. We're breaking down the revolutionary style-based generator architecture that permanently changed how generative adversarial networks synthesize images.
Right.
The goal for this deep dive is to understand how researchers finally managed to, peek inside the black box of these models, how they mathematically disentangled the underlying factors of variation, and how they ultimately gave us intuitive, scale-specific control over generated imagery.
Which was huge. I mean, to really set the stage for this, we got to look at the landscape of generative modeling right before this paper dropped.
Right, because things were moving fast, but there was a massive bottleneck, right, in how we actually controlled the outputs.
There certainly was. If you look at the era immediately preceding this research, the focus was heavily on resolution and sheer visual fidelity.
Yeah, just making things look good.
Exactly. We had seen incredible breakthroughs, most notably progressive growing techniques.
Oh, right.
Where they allowed networks to stabilize training by starting at very low resolutions.
Like 4x4 pixels.
Yeah, 4x4, and then slowly adding layers to build up to high resolution images. But despite those leaps in visual quality, the internal mechanics of the generators were essentially black boxes.
Yeah.
Researchers lacked a fundamental understanding of where specific features even originated during the synthesis process.
So they're getting these great images, but they don't know how the math is actually getting them there.
Right. For instance, highly stochastic features, the exact placement of individual hairs, or the specific distribution of skin pores.
Random stuff.
Exactly. Those seem to emerge entirely unpredictably from the network's internal activation.
Wow.
And more importantly, the latent space itself, the mathematical domain where these generated images originate as coordinate points, was poorly understood and highly entangled.
So we had these incredibly powerful engines capable of rendering photorealistic faces, but we had absolutely no steering wheel.
None at all.
We couldn't isolate a specific feature without mutating the entire output.
Yeah, you touch one thing, everything breaks.
Which brings us to the core thesis of the research we're analyzing today for you, the listener. By omitting the traditional input layer entirely,
Literally throwing it at.
and borrowing concepts from style transfer literature, this architecture automatically separates high-level attributes from stochastic variations. Proving definitively that the traditional feed-forward generator architecture is mathematically inferior to a style-based design.
It really was a paradigm shift. I mean, it forced the entire field to rethink the structural assumptions of image synthesis.
Yeah.
But to truly grasp the magnitude of this shift, we first need to examine the specific mathematical flaws of the traditional architecture that everyone was using at the time.
Right. Let's get into the entanglement problem.
Exactly. The fundamental flaw of the era's models boils down to what we call that entanglement problem.
Okay, so traditionally, how did it work?
Traditionally, the generative process begins with a latent code.
Right.
This is a random vector of numbers, typically denoted as Z, which is drawn from an input latent space called capital Z.
Okay, so a random bunch of numbers.
Yeah. And in a standard traditional architecture, this random vector Z was fed directly into the first layer of a feed-forward neural network.
That was the front door.
That was the singular entry point for the network's initial instructions.
And I mean, on the surface, that traditional pipeline seems entirely logical.
It does.
You provide the network with a randomized numerical starting point, and it deterministically calculates its way to a two-dimensional matrix of pixels.
Right.
But mathematically speaking, why is feeding that random vector directly into the first layer a structural dead end?
Because it creates an inescapable problem known as the probability density trap.
Okay, unpack that for us.
So the input space Z is typically structured as a uniform or normal distribution.
Like a perfect sphere of probability.
Right. A perfectly symmetrical, mathematically pristine space. But here's the catch. It must be mapped to the probability density of the training data. If you draw a random sample from Z, the distribution of those generated samples has to perfectly mirror the highly irregular, chaotic distribution of features in the real-world dataset you use to train the network.
And the real world is definitely not a perfect sphere.
Not even close. The visual manifold of the real world is incredibly complex and unevenly distributed.
Okay, so if the network is forced to mirror the real world, and the real world is messy, How does that mathematically break the generator?
Well,
Let me give you, the listener, an analogy to visualize this clearly.
go for it.
Imagine your training data is missing a specific combination.
Okay.
Like long-haired men.
Good example.
You're training on faces, and for whatever reason, that specific intersection of male and long hair just isn't in your data set.
Right.
Because the network can't sample invalid combinations that the discriminator would reject, it physically warps and bends the mapping from that perfect latent space to the image features.
It has to route around the empty space.
Exactly. It tangles the masculinity dial and the hair length dial together. If you turn one, the other gets yanked along with it.
That's exactly it. It fundamentally tangles the representations together. In your example, it fuses the mathematical representation of masculinity with the representation of hair length.
So if you try to adjust it,
If you attempt to navigate that space and move along the axis to give a generated male face longer hair, the other features get yanked. The face might suddenly morph into a female face.
because that's the only way the math can resolve the missing data.
Right. The network's internal mapping has violently curved to route around the empty space where long-haired men should exist.
So true understanding, true control in a generative model demands linear subspaces.
Yes. Disentanglement.
You want a mathematically disentangled representation where moving along one specific axis controls exactly one factor of variation, completely independent of the rest.
Exact.
You want to adjust hair length without mutating the gender, the lighting, or the pose.
But if the input space Z is mathematically forced to mimic the warped, uneven distribution of the training data,
Linear disentanglement is structurally impossible.
impossible. The features are inextricably tangled at the very first mathematical operation.
That's wild. The foundational constraint of the traditional architecture made true control an impossibility from step one.
Yeah, and the researchers realized they had to completely abandon that traditional front door of the network.
Which leads us to the radical architectural redesign at the heart of this paper. They completely removed the input layer from the synthesis network.
They just threw it out.
Instead of feeding the latent code Z into the first convolution layer, the image synthesis network starts from a learned constant.
Right.
Specifically, a 4x4x512 tensor.
And that is a massive departure from standard practice.
Yeah, explain that.
So the synthesis network begins its process with a rigid block of numbers that is optimized during the training phase.
Correct.
But once it's trained, it becomes the exact same starting tensor for every single image the network ever generates.
Wait, the exact same start for every image.
Every single one. The network uses this constant as a stable, unvarying structural canvas.
That feels so counterintuitive.
It was. It was a highly counterintuitive discovery that a synthesis network could produce meaningful, diverse, and photorealistic results without receiving any direct variability through a traditional first layer.
But, okay, if they threw out the front door,
Yeah.
the random Z vector still has to go somewhere, right? You can't just delete the input, start with a constant block of data, and expect a diverse output.
No, you can't.
So how did they bridge the gap between the random latent code and this new blank canvas?
To supply the actual generating instructions, they introduced a secondary structure called the mapping network.
Okay, the mapping network,
Yeah.
denoted as F.
Right, F. And this is an 8-layer, multi-layer perceptron, an MLP.
Okay.
It takes the initial 512-dimensional random vector Z from the highly entangled Z space and runs it through 8 fully connected layers.
And what comes out the other side?
The output is a brand new 512-dimensional vector called W.
Little W.
Yes, little w, which resides in an entirely new intermediate latent space named W space, capital W.
Okay, so we're translating Z into W, but why specifically an 8-layer MLP? It seems like a significant amount of computational overhead just to translate a vector before the actual image synthesis even begins.
It is overhead, but it's necessary.
What is the mathematical advantage of this W space that makes the 8-layer translation worth it?
The advantage is absolute freedom from the training data distribution.
Oh.
Remember how the original Z space must support sampling according to a fixed distribution, usually a Gaussian sphere?
Right, the probability trap we just talked about.
Exactly. But the intermediate W space does not have this restriction. Its sampling density is induced entirely by the learned, piecewise continuous mapping of the neural network.
So this is the aha moment for you, the listener.
Yeah.
Because W space isn't tethered to a fixed probability density, it's allowed to unwarp itself.
Yes.
It doesn't have to violently curve its internal representations to route around the missing gaps in the training data, like those missing long-haired men.
Precisely. The network naturally wants to disentangle the representations because it makes generating realistic images easier.
It naturally wants to.
Yeah. When factors of variation are clean, separate, and linear, the math required to map them to realistic image features is vastly simpler.
So it's taking the path of least resistance.
Exactly. By inserting this 8-layer intermediate playground, you give the network the mathematical capacity to straighten out those curved, tangled mappings unsupervised.
Wow.
It separates the features simply because an unwarped representation is the most efficient way to optimize against the discriminator.
That's brilliant. And they proved this empirically, didn't they?
They did. They applied it to baseline architectures. They took a standard progressive GAN from that era, evaluated it using the Frichet inception distance, or FID.
The standard quality score.
Right. And then they grafted this mapping network and intermediate W space onto it.
And the FID scores immediately improved.
Dramatically.
Yeah.
Along with the separability of features.
Demonstrating that the traditional input space was actively bottlenecking the generative capabilities of the older models.
Exactly.
Okay, so we now have this cleanly unwarped, disentangled vector. We're existing in its intermediate space.
Right.
But we still have a disconnect.
The canvas.
Right. We have the W vector, and we have that blank 4x4 canvas in the synthesis network. How do these two components actually interact to construct the image?
This is where the researchers borrowed a highly effective operation from style transfer literature.
Oh, I love this part.
Yeah, it's called adaptive instance normalization, or AdaIN.
AdaIN, the conductor of style.
The disentangled vector DELA interacts with the synthesis network strictly through these AdaIN operations, which are embedded after every single convolution layer.
Okay, let's drill down into the mechanics of AdaIN, because this is the engine of the entire architecture.
It really is.
How does it translate a vector into a visual style, and why are the specific mathematical operations of scaling and shifting so crucial here? Let's do the math in plain English.
Sure. So first, the network takes the disentangled vector W and passes it through learned affine transformations.
Refined transformations.
Right. An affine transformation is a geometric operation that preserves lines and parallelism, essentially. It involves a scaling operation, which is multiplication, and a shifting operation, which is addition.
So scaling and shifting.
Exactly. These transformations specialize the W vector into specific styles, which are just discrete sets of scales and biases.
Got it.
Now, look at the synthesis network itself, which is processing spatial data from the 4x4 constant all the way up to a high-resolution output. After a convolution layer produces a feature map, the AdaIN operation intercepts it.
And what is the exact sequence of operations when AdaIN intercepts that feature map?
It executes two specific steps. First, it normalizes each channel of the feature map separately.
Okay.
It calculates the mean and variance of the spatial features and completely neutralizes them. It reduces the entire feature map to a 0 mean and unit variance.
Wait, so it scrubs away any stylistic information that was just computed?
Aggressively scrubs it away, leaving only the raw, normalized spatial structure.
Wow.
Then comes the second step. It applies new scales and biases derived from the specialized W vector.
The style.
Right. It multiplies the normalized features by the style scale and adds the style's bias.
So by forcing a 0 mean and unit variance, the network is fundamentally destroying the stylistic information for the previous layer, retaining only the spatial structure.
Yep.
That's a highly aggressive regularization technique when you think about it. The network computes features. AdaIN wipes the statistical slate completely clean and then stamps a new style onto that raw structure.
Exactly.
And it repeats this sequence after every single convolution.
Yes. And that aggressive neutralization is exactly what gives this architecture its unprecedented power.
Why? What does this all mean for control?
Because AdaIN normalizes the original statistics of the feature map before applying the new style, each style vector only controls that one specific convolution layer. The moment the data passes to the next layer and undergoes the next convolution, the next AdaIN operation will immediately neutralize it again.
It wipes it out.
Right. The stylistic effects are strictly localized.
Because in a traditional model, altering the input vector slightly sends a mathematical ripple through the entire feed-forward network, right?
A huge ripple, mutating features at every scale in unpredictable ways.
But by injecting the intermediate style W, fresh, at every single scale of the image, and scrubbing the statistics between injections, you completely isolate the effects.
Yes, you contain them.
That localized control naturally enables a fascinating training technique, that the researchers call style mixing.
Style mixing is a vital regularization method.
Okay, break that down for us.
If you use a single latent code for the entire network during training, the network might assume that the styles applied at early layers are always mathematically correlated with the styles applied at later layers.
Like if it always sees coarse features and fine features from the same vector together.
Exactly. To break that assumption, the researchers force the network to mix distinct latent codes.
How does that work in practice?
During training, a certain percentage of the generated images are created using two completely independent random latent codes, Z1 and Z2.
Both vectors are processed through the mapping network independently.
Right, yielding two separate intermediate styles, W1 and W2.
So how is the network forced to integrate both of them into a single synthesis pipeline?
The synthesis network begins processing the image using the styles derived from W1.
The first code.
Right. Then, at a randomly selected crossover point within the network's layers, it abruptly switches and applies the styles derived from W2 for all remaining layers.
Just a hard pivot mid-generation.
Exactly. This operation forces the network to decouple adjacent layers. It has to learn that the structural parameters defined at the 4x4 resolution cannot dictate or restrict the stylistic parameters applied at the 64x64 resolution.
This explicit decoupling is what gives us scale-specific control.
Yes.
And the researchers rigorously mapped out exactly what these injected styles control at different spatial resolutions.
The visual taxonomy they discovered is incredible.
Let's break down the distinct scales for the listener, starting with the coarse styles.
The coarse styles correspond to the lowest resolutions of the synthesis network, specifically the layers operating at 4x4 and 8x8 spatial dimensions.
Okay, the foundation.
Because these layers establish the foundational geometry of the image, the coarse styles control the highest level global aspects of the generated subject.
So what happens if you alter the coarse styles while leaving the rest of the network untouched?
You fundamentally shift the overarching structure, the physical pose of the head, the foundational shape of the face.
The general trajectory of the hair.
Right, and the presence of major structural accessories, such as whether the person is wearing eyeglasses.
So they dictate the macro-level geometry.
Exactly.
As we move further down the network architecture, we reach the middle styles, which operate at the 16x16 to 32x32 resolutions. How does the stylistic control shift at this scale?
At the middle styles, the global geometry is already locked in by the earlier layers.
Right.
So the control shifts to smaller scale facial features and specific structural textures.
Like what?
This resolution dictates specific hairstyling, the way strands curve or fall, as well as distinct facial expressions. And notably, whether the eyes are fully open or closed.
Oh, that's interesting. So if you execute a style mix, combining the coarse style of one latent code with the middle style of another,
the generated face will retain the overarching head pose and face shape of the first code,
but will seamlessly inherit the open eyes and specific hair curl pattern of the second code.
Exactly. It's perfectly modular.
Wow. Finally, we reach the high-resolution end of the network, the fine styles, spanning from 64x64 all the way up to 124x2024.
The fine styles primarily govern the color scheme and the microscopic structure of the image.
The details.
Right. They dictate the exact pigmentation of the eyes, the precise hex code of the hair color, the localized lighting environment, and the microtexture of the skin.
So the identity, geometry, and structural features remain completely untouched, while the fine styles apply a specific palette and microtexture over that established geometry.
It's an incredibly precise stratification of visual features.
It is. But to fully understand the realism this network achieves, we have to look at the features that fall outside the realm of global or even localized structural control. Exactly. We have to discuss how the architecture embraces explicit noise injection for pure stochastic variation.
Stochastic variation is a critical component of photorealism that earlier architectures struggled with immensely.
Because it's a huge burden, right?
It is. Think about it. While a subject's identity, pose, and eye color are deterministically defined, countless microscopic aspects of a human portrait are purely chaotic and random.
The exact spatial placement of individual hair strands.
Right. The precise layout of skin pores, the irregular distribution of freckles, or the scattering of stubble.
These are not defining features of identity, they are stochastic noise.
And from a computational standpoint, forcing a deterministic neural network to calculate the exact spatial coordinates of every single freckle or hair strand based solely on a high-level latent code is incredibly inefficient.
It creates a massive burden of stochasticity.
Exactly. In traditional feed-forward generators, the only source of variability was the single input vector at the very beginning of the network.
The z-vector we talked about.
Right. By the time that network is rendering the final 124 by 124 output, if it needs to generate a random pattern of skin pores, it has to consume its own representational capacity to contrive spatially varying pseudo-random numbers from earlier low-resolution activation.
And mathematical networks are inherently deterministic. They are incredibly poor at faking localized randomness.
Very poor. This limitation is why older generative models frequently suffered from severe periodic artifacts.
Oh, those ugly, unnatural, repeating checkerboard patterns.
Yes, in the textures of hair or skin where the network failed to hide the mathematical periodicity of its own convolutions.
So how did the researchers bypass this limitation? What was the elegant fix that allowed them to offload that burden of stochasticity without compromising the global structure?
The solution was elegantly direct, explicit noise injection.
Okay.
The researchers added single-channel images of uncorrelated Gaussian noise directly into the network after every single convolution layer.
So they are piping raw, spatially uncorrelated static directly into the feature maps alongside the deterministic style inputs.
Yes, raw static. And the network utilizes that static as the foundational material to render microscopic, randomized details.
The visual evidence of this division of labor in the paper is striking.
It really is the proof in the pixels.
Let me describe this for you, the listener. If you run the generator and synthesize a specific face, and then generate it again using the exact same latent codes for both the coarse and fine styles.
But you randomize the explicit noise inputs.
Right. The results perfectly illustrate the architecture's internal logic. The identity remains mathematically identical. The pose, the lighting, the eye color are all perfectly preserved.
But upon zooming in, the placement of individual hair strands has completely shifted.
The freckle distribution is uniquely randomized.
Even the tiny, chaotic, specular reflections bouncing off the character's irises are entirely distinct.
The network's ability to organically compartmentalize these inputs is fascinating.
Well, it makes sense mathematically. The style vectors, fed through AdaIN, apply to entire feature maps uniformly via scaling and biasing,
making them perfectly suited for global structural control.
Exactly. Conversely, the explicitly injected noise is applied independently to individual spatial pixels.
So the network rapidly learns during optimization that attempting to utilize pixel-level static to control a global geometric feature like the pose of a jawline results in spatially inconsistent, fractured outputs,
which the discriminator easily identifies as fake and penalizes.
So, entirely unsupervised, the network learns to delegate high-level identity to the styles and restricts the chaotic microscopic details purely to the noise inputs.
It's beautiful. You can observe exactly how critical this noise is by performing an ablation study.
What happens if you artificially zero out the explicitly injected noise during inference?
The generated image immediately degrades. The researchers note that the output takes on a featureless, painterly appearance.
Painterly?
Yeah, the microtextures of the skin vanish, leaving an unnaturally smooth, almost plastic surface. And the individual strands of hair blur together into solid geometric clumps.
Wow. Furthermore, the noise injection exhibits the exact same scale-specific localization as the styles, right?
Yes, it does. Coarse noise injected at the lower resolutions generates large-scale stochastic effects,
such as the overarching curl pattern of thick clumps of hair.
Right. While fine noise injected at the highest resolutions controls the finest microtextures, like individual skin pores.
The architecture cleanly dissects the visual world into deterministic structure and stochastic detail.
It does.
However, proposing an architecture that organically disentangles these features is only half the battle. In academic research, visual results must be substantiated by rigorous mathematical proof.
Yeah, I gotta bring the receipts.
The researchers needed to quantify the disentanglement of their new W space compared to the traditional Z space, but this presented a major evaluation problem.
A huge hurdle. Because measuring latent space disentanglement historically required an external encoder network, didn't it?
Right. A secondary model trained specifically to take a finished image and reverse engineer it back into its originating latent coordinates.
But this architecture didn't include an encoder, and the authors deliberately avoided, tacking on an external network just to validate their generator.
So they required evaluation metrics that could be calculated directly from the generator's forward pass without relying on specialized external architectures.
Exactly. To solve this, they introduced two novel automated metrics. The first is perceptual path length, or PPL.
Okay, let's break down the underlying mathematics of perceptual path length.
Sure.
How does moving between 2 points in a latent space reveal whether that space is entangled or unwarped?
PPL is fundamentally based on the concept of latent space interpolation.
Meaning moving smoothly between 2 points.
Right. If a latent space is highly entangled, like a traditional Z space, navigating the mathematical path between two distinct latent points, say, transitioning from a latent code representing a young subject to one representing an older subject, results in severe nonlinearities.
Why is that?
Because the mapping from Z to the image space is violently curved to accommodate the training data's density trap, a straight mathematical line through Z space actually cuts across violently shifting visual features.
Oh, so during the visual interpolation, features that do not exist in either endpoint will suddenly flash into existence and vanish.
Exactly. A completely smooth mathematical transition in an entangled space results in a chaotic, nonlinear visual transition.
So how do you formally measure the length of that visual chaos?
You measure it by executing tiny incremental geometric steps along the interpolation path between the two latent points.
Microsteps.
Right. For traditional Z space, this is calculated using spherical interpolation, or SLIRP, because Z is a normalized sphere. For W space, standard linear interpolation is used.
Okay.
At every microstep along this path, you generate the corresponding image. You then compute the perceptual distance between the image at the current step and the image at the previous step.
And how do you measure perceptual distance accurately? You can't just subtract the pixels.
No, pixel subtraction is terrible for human perception. They utilize VGG16 embeddings.
VGG16.
Yeah, VGG16 is a convolutional network trained on ImageNet. Its internal activations are widely proven to correlate strongly with human visual perception of image differences.
Right.
By calculating the VGG16 distance between every adjacent image on the path and summing them up, you arrive at the total perceptual path length.
So a shorter cumulative PPL indicates that the visual transitions between the microsteps were minimal and smooth.
Exactly.
Which proves that the underlying mathematical space is less curved and therefore highly disentangled.
Yes. And the empirical results from the paper were definitive. The intermediate W space produced drastically shorter perceptual path lengths compared to the traditional Z space across multiple configurations.
It mathematically verified that the mapping network successfully unwarped the latent representations.
Which brings us to their second novel evaluation metric, linear separability.
Okay.
This metric approaches the concept of disentanglement from a geometric classification perspective.
Explain the concept here. Linear separability examines the fundamental geometric organization of the latent space, right?
Right. The core question is, can you bisect the high-dimensional latent space with a single flat mathematical plane, a hyperplane, such that all generated images possessing a specific binary attribute fall entirely on one side of the plane, and all images lacking it fall on the other?
Give us an example.
For example, can you define a hyperplane where every latent point on the positive side generates a face wearing glasses, and every point on the negative side generates a face without glasses?
So if the space is genuinely disentangled, individual attributes should occupy cleanly separated linear regions.
Yes, but if the space is entangled, the attributes will be chaotic and inseparable by a flat plane. You'd need a super wavy, complex boundary to separate them.
So how do they empirically measure this separability?
They leveraged auxiliary classification networks. They generated hundreds of thousands of images and utilized external classifiers trained on the 40 distinct binary attributes of the Celeva HQ dataset to label every generated image.
Okay, so they have a massive pile of labeled coordinates now.
Right. They then took the corresponding latent coordinates for those images and attempted to fit a linear support vector machine, or SVM.
An SVM?
Yeah, an SVM to predict the classifier's label based purely on the latent point's position in the space.
How do they score that?
The critical calculation here relies on conditional entropy.
Okay.
They calculate the entropy of the actual predicted classes given the specific region of the latent space determined by the SVM hyperplane.
Meaning?
Conditional entropy entropy essentially quantifies the amount of additional information required to determine the true attribute of a sample, given its spatial relationship to the dividing plane.
So a lower conditional entropy value indicates that the hyperplane successfully segregated the attributes,
proving high linear separability.
And what were the results?
Once again, a landslide. The intermediate W space exhibited vastly superior linear separability compared to Z space across the tested attributes.
They successfully proved the superiority of the W space using completely self-contained metrics.
Yep.
But verifying an architecture's mathematical properties requires testing it against highly complex, unforgiving data. To push the boundaries of their new generator, the researchers introduced a phenomenal new dataset, didn't they?
Oh yeah, Flickr Faces HQ or FFHQ?
Raising the data standard entirely.
The release of FFHQ was a watershed moment for the generative modeling community. It consisted of 70,000 highly curated, uncompressed human faces at an unprecedented 124 by 1024 resolution.
And it vastly outpaced older data sets, right?
It dwarfed older standards like Celeb HQ in almost every conceivable metric of diversity. It contained massively wider variations in age, ranging from infants to the elderly, immense diversity in ethnicity, lighting environments, and viewpoints.
Not to mention accessories.
Right. Comprehensive coverage of obscure accessories, varied eyewear, and headwear.
But introducing that level of chaotic diversity into a training pipeline immediately surfaces a notorious generative modeling hurdle, the density problem.
Yeah, the density problem is unavoidable in highly diverse datasets.
Explain that for the listener.
It arises from the fact that the extremes of human appearance are statistically rare. Areas of low density in the training distribution, for example, the intersection of specific extreme age, unusual lighting, and obscure headwear contain very few examples.
Right.
Because the discriminator has minimal data to penalize a generator in these sparse regions, the generator models them poorly.
So what happens if you land there?
If you sample a random latent code that happens to map to one of these low-density outlier regions, the generator produces highly distorted, geometrically broken, or unnatural images.
So how do you fix that? To mitigate this without permanently crippling the network's capacity, the researchers adapted a clever workaround called the truncation trick.
Specifically engineered for their new W space.
Right. The mathematics behind this trick are incredibly clever. First, you calculate the center of mass of the entire W space.
By finding the exact mathematical centroid of all mapped styles.
Which essentially looks like the ultimate average face of the entire 70,000 image dataset.
Exactly. Having established that centroid, you intercept a given random vector of before it reaches the synthesis network.
Instead of passing it directly,
you scale the vector, mathematically pulling it closer toward that center of mass by a defined truncation parameter.
Oh.
By systematically pulling vectors away from the extreme low-density perimeters and forcing them into the high-density, well-modeled central regions of the space.
You drastically increase the average photorealism and structural integrity of the output?
By pulling everything toward the centroid, we are essentially trading extreme diversity for guaranteed fidelity.
We lose the obscure edge cases, but we ensure the output adheres to a realistic human manifold.
But exploring this centroid mathematics led to one of the most conceptually fascinating, spooky quirks of the entire paper.
The antiface.
Yes.
The antiface.
The antiface is a direct visual manifestation of the linear disentanglement we've been discussing. If you can mathematically scale a vector toward the centroid to make it more average, you can also apply a negative scaling factor.
Pushing the vector directly away from the centroid.
Right. Continuing along the exact same linear trajectory, but into negative space. And that generates the subject's exact mathematical opposite.
High-level attributes literally flip.
They do.
If your initial positive latent coordinate generates a young bearded man facing the left edge of the frame without eyewear, applying a negative scale to that exact coordinate generates an elderly woman without facial hair facing the right edge of the frame wearing thick glasses.
Gender flips, age inverts, structural accessories mirror.
It perfectly proves that the mapping network has successfully organized these complex visual concepts along continuous, easily navigable linear axes that intersect through the space's center of mass.
It's a spectacular visual proof of their mathematical claims.
It really is. Now, beyond human faces, this architecture wasn't just a one-trick pony. To prove the architecture was fundamentally robust and not merely overfitted to the domain of human faces, they subjected the generator to other highly complex, structurally distinct datasets.
Specifically leveraging the LSUN datasets, including bedrooms, cars, and cats.
Analyzing how the style vectors map to fundamentally different objects really highlights the universal applicability of AdaIN.
Yeah, the hierarchical separation of control remains completely intact regardless of the training subject.
Let's look at the LSUN bedrooms dataset, for example.
In bedrooms, the course styles operating at the 4x4 and 8x8 resolutions rigidly dictate the macro geometry of the room and the overarching camera viewpoint.
Okay.
The middle styles populate the room, selecting the specific architecture of the windows and the exact type of bed.
And the fine styles.
Finally, the fine styles operating at the highest resolutions define the granular color palettes of the walls and the precise microtextures of the fabrics on the furniture.
It just perfectly maps over. What about the cars dataset?
The CARS dataset provided an even more nuanced look at how the network handles the division between deterministic geometry and stochastic noise.
How so?
The coarse and middle styles completely govern the make, model, chassis geometry, and global orientation of the vehicle.
Makes sense.
The explicit noise inputs, meanwhile, handle the chaotic elements, the randomized detailing of the background asphalt, and the highly complex, unpredictable specular scattering inside the car's headlamp casings.
But there was an incredible observation there.
Oh, yeah. The orientation of the car's wheels never rotated based on the stochastic noise inputs.
The network mathematically inferred that while a headlamp reflection is chaotic, a wheel is a rigid geometric component intrinsically locked to the structural chassis of the car.
It refused to delegate wheel rotation to the random noise channels.
That is so smart. But speaking of unpredictable variables, the researchers dedicated specific attention to the sheer difficulty of the LSU CANs dataset.
Yeah, modeling cats represents a worst-case scenario for generative alignment.
Why is that?
Unlike the FFHQ dataset, where human faces are rigidly centered and cropped, or the CARS dataset, which features consistent rigid geometry, photographs of cats possess extreme intrinsic variation.
Oh, right. Feline poses are highly fluid and non-rigid.
Exactly. The zoom scales of the photography vary by orders of magnitude, and the background environments are entirely chaotic and unconstrained.
Despite that massive structural chaos, the style-based architecture successfully imposed a hierarchy. My absolute favorite detail from their analysis is that while the coarse styles define the breed and the general posture,
like an orange tabby sitting on a rug.
Right. The stochastic variation uniquely controlled the randomized positioning of the cat's individual paws.
Yes. The noise dictated whether a specific paw was slightly tucked, splayed, or hovering.
That's amazing. Looking at the complete picture, the unwarping of W space, the AdaIN integration, the localized explicit noise, and the rigorous mathematical proofs via PPL and separability. What is the ultimate legacy of this architecture within the broader field of generative modeling?
Its legacy is foundational. This research was not a minor iteration. It functionally invalidated the previous state-of-the-art.
It improved state-of-the-art fresh-head inception distance scores by almost 20%, didn't it?
Over the most advanced traditional feed-forward architectures, yes. But beyond the metrics, it proved definitively that traditional latent space mappings were inherently bottlenecked by the probability density trap.
Yeah.
By decoupling high-level deterministic attributes via AdaIN from pixel-level stochastic effects via explicit noise injection, it transformed the generator from an unpredictable black box into a mathematically tunable engine.
It provided a framework for localized, interpretable control that influenced the structural design of virtually every generative model that followed.
It fundamentally reshaped our understanding of how mathematical spaces represent visual reality.
Which brings us to the final segment of our deep dive. Novel notions.
I love this part.
Before we begin, I must explicitly state for you, the listener, that the concepts discussed in this closing segment are purely theoretical and intended strictly for entertainment purposes only. We are taking the verified mathematical mechanics of the architecture we just analyzed and extrapolating them into highly speculative, though logically consistent, future research domains. Expert, what is your first novel notion inspired by the mechanisms of this paper?
Idea 1. W-space macroclimate simulation.
Oh, wow. Okay.
Consider applying this exact architectural paradigm, the mapping network, intermediate spaces, and AdaIN localization, not to visual pixels, but to high-dimensional global meteorological arrays.
Climate data.
Right. Current predictive climate algorithms face an immense entanglement problem. Variables are deeply chaotically linked. A fractional shift in oceanic temperature impacts barometric pressure, which alters localized humidity, cascading into a tangled web of overlapping predictions.
So what What if we fed raw historical global climate data into an 8-layer mapping network to construct a meteorological W space?
Exactly. By decoupling the variables, the mapping network would naturally separate the global deterministic climate drivers from the localized stochastic weather events.
How would the scales break down?
The core styles would encapsulate the macroscopic, slow-moving planetary variables, macrooceanic currents like El Niño, global atmospheric carbon parts per million, and foundational solar radiation levels.
And the fine styles?
Fine styles and explicit noise injections would control the localized chaotic events, specific regional storm formations, microclimate humidity fluctuations, or individual localized lightning strikes.
The experimental implications of that decoupling are staggering.
Yeah.
You could execute a literal style mix of historical climate eras.
Yes.
You could lock in the pre-industrial climate as your foundational core style, establishing the global temperature baselines and macrocurrents of the 1800s.
Right.
You could then inject the fine styles and localized stochastic noise of modern extreme weather patterns into that historical baseline.
Exactly.
You could isolate and test exactly how a specific hyperlocalized modern hurricane formation parameter behaves when mathematically dropped into an unwarped, disentangled pre-industrial macroclimate, entirely avoiding the deeply entangled feedback loops that bias current predictive models.
It would allow us to mathematically isolate the impact of specific stochastic events against differing global structural baselines.
That is a phenomenal extrapolation of the AdaIN concept. I have idea too. And it pivots the architecture away from numeric arrays and applies it to semantic generation. Cognitive AdaIN for large language model.
Oh, applying it to text. Okay.
Right. Current LLMs generate text in a linear, autoregressive manner, calculating probabilities word by word or token by token. What if an LLM generated entire concepts hierarchically by mapping a complex prompt into a cognitive semantic W space?
That requires a fascinating reinterpretation of spatial resolution as semantic depth. How would you map the scales of control to textual structures?
Well, the core styles, injected at the foundational layers of the semantic synthesis network, would rigidly lock in the indisputable facts and the core logical framework of the argument. That is the structural geometry of the essay.
Okay, the facts are locked.
Then the middle styles, injected later, would dictate the syntactic structure and vocabulary level, determining whether the geometry is populated with the lexicon of a peer-reviewed academic journal or a casual blog post.
And the noise?
Finally, the explicit noise injection at the highest layers provides the purely stochastic elements of language, the specific colloquialisms, the randomized sentence length variations, and the idiosyncratic human tone.
The utility of that separation is profound.
Isn't it?
You could generate a highly complex analytical document, lock the factual geometry in place via the coarse semantic styles, and merely randomize the final noise injections to produce thousands of structurally identical, factually immutable, but textually unique variations of the document's voice.
Infinite structurally identical variations.
Because the core facts are mathematically insulated from the stochastic word choice generation at the higher resolutions, it would theoretically eliminate factual hallucinations entirely.
The network is structurally prevented from allowing a creative stochastic vocabulary choice to alter the underlying logical geometry.
You constrain the creativity strictly to the superficial layers, completely isolating the logic. It's AdaIN applied directly to thought structures.
Exactly. And this brings us to the conclusion of our deep dive today. Expert, leave us with one final provocative thought regarding the implications of this research.
I would say this. If an artificial neural network, when provided with the mathematical freedom of an unconstrained intermediate space, naturally converges toward untangling and cleanly separating the variables of our visual world in order to effectively process them, what does that mathematical preference reveal about the deeply entangled, inherently biased structures of the real-world datasets we mandate these models to learn from?
A deeply compelling question regarding how data reflects reality. Thank you to you, the listener, for dedicating your time to this deep dive. Until next time.